Hello, everyone, and welcome to week 12. This week, we're going to discuss chapter 14, which is on groundwater. And just as a reminder, if any of you ever have any questions about groundwater or surface water for that matter, I am a hydrogeologist, and so this is kind of my specialty. And so, feel free to ask any questions about the material, but also about career opportunities, especially for those of you that are geology majors. So why is groundwater important? It's the largest reservoir of fresh water that's available to humans. So that's a pretty big deal. And what is groundwater? Well, it's found in the pores of soil and sediment, as well as narrow fractures in bedrock. So it's just water that exists within the subsurface. And not only is it the largest reservoir of fresh water available to us, but it's also 0.6% of the entire hydrosphere. So let's look at Earth's fresh water in a little bit more detail in terms of a share of the total fresh water on Earth and a share of all liquid fresh water on Earth. So as far as a share of the total volume of fresh water on Earth, you can see on the chart on the left that groundwater actually makes up 14.6% of this volume, which is a greater volume than any reservoir of fresh water outside of ice sheets and glaciers. And then if we remove ice sheets and glaciers and just talk about liquid fresh water, you can see on the chart on the right that groundwater actually comprises 94% of all liquid fresh water on Earth. So, not only is it the highest volume of water that's available to us humans, but it's the highest volume of water that's available to us by far. Groundwater also has significant geological importance. So for example, groundwater acts as an erosional agent and dissolves soluble bedrock, for example, limestone. If any of you have ever been caving or seen and saw photographs of any caves, a lot of caves are limestone because limestone is a very soluble variety of bedrock. Calcium carbonate is easy to break down, or water can break it down easily. In fact, beyond just limestone, water is often referred to as the universal solvent. So we talked about this a little bit when we talked about erosion. But it's important to remember here because all groundwater or all water in the subsurface is also acting to dissolve soluble bedrock, sediment, etc. Groundwater also serves as an equalizer of stream flow. That's some interesting wording that I chose there, but what that really means is that groundwater and surface water are connected to one another in many locations. And this is very important. In some states, like for example, New Mexico, water law suggests that groundwater and surface water are disconnected from one another. And that results in crazy things like, the Rio Grande near the southern border on New Mexico. You have a bunch of farmers with pecan orchards that have wells, let's say 20 yards away from the Rio Grande. They're just pumping those wells like crazy because they have groundwater rights. And, according to water law, they're not taking water from the Rio Grande, but in fact, that is what they're doing. And that's why there's so much groundwater there, is they're effectively sucking water up from the river and calling it groundwater. In Idaho, we have conjunctive management, which means that we consider groundwater and surface water to be resources that are hydrologically connected to one another. And this is really important, that our water law is designed in this way so that we stand a chance at maintaining, sustainable stream flow and sustainable groundwater levels for both human use and for natural ecosystems. So for example, in the watershed or basin or catchment that I spend most of my time in when working for Idaho Department of Water Resources, that basin is the Lemhi Basin up near Salmon, Idaho. My group works together with the local water users who both divert water from streams and pump groundwater to irrigate their crops. But we work with them to make sure that water law there both allows them to get the water that they need to irrigate and allows for sustainable fisheries, so endangered species of fish like Chinook, steelhead, and bull trout can make a go of it up there. So where does groundwater come from? Well, most of it is the result of precipitation that infiltrates through the soil, through the zone of soil moisture. And when I say precipitation in this case, I mean that to mean both precipitation in liquid and solid form. It's just that if the precipitation is in solid form, for example, snow, then it takes longer for that water to infiltrate into the soil and make it to the groundwater reservoir because the snowpack has to melt. So it's actually the snow melt ultimately that's entering into the zone of soil moisture. The zone of soil moisture is a zone where water is held by molecular attraction onto soil particles in the near surface zone. This is also known as the vadose zone. That's another name for it that's used more commonly amongst geoscientists. And so if you think about the pores, if you think about the pores within the soil, after you have a precipitation or a snow melt event, water doesn't just simply drain through that soil and go deeper into the earth. Some of it does that, but another portion of the water clings on to soil particles from molecular attraction. So I won't get into the details of that molecular attraction here because this class is mostly focused on physical geology, but just know that there is a chemistry-based reason why water is attracted to these soil particles and why it remains there long after a precipitation event or a snowmelt event. So for example, if you were to go up into the Boise foothills and take a soil core, you don't have to go very many centimeters down into the soil, even if it's been months since it rained, to find some soil moisture. And in fact, even if you were looking at soil in the first 10 centimeters of the soil column, you'll still find some soil moisture. I know this for a fact because in grad school I went out and cored a bunch of soil and extracted the water to analyze the isotopes within that water. And it was amazing, like the conditions in which you would still find some soil moisture. So anyways, that was kind of an aside, but interesting to note. So the zone of soil moisture is what's used by plants. So plants root into the zone of soil moisture, and then they take up that soil water and transpire it as part of the process of photosynthesis. And then through transpiration, that water evaporates from the stomata, or sort of pores or openings within the leaves of the plant, and it evaporates directly back to the atmosphere as part of the water cycle. Um, so below that zone, the vadose zone, is, if you're moving down into the subsurface, is the zone of saturation. And this is the zone where all of the pore spaces are completely filled with water. So no longer do you have, just some particles of water clinging on to soil particles due to molecular attraction, but literally the pore space is completely filled. And this zone of saturation is what's known as groundwater. So when I talk about groundwater, I'm not talking about water within the vadose zone that's clinging onto soil particles. I'm talking about the zone in the subsurface where soil pores are filled with water. So a lot of you, especially those of you with wells or if you know people with wells, are probably familiar with what the water table is. So it's the upper limit of the zone of saturation, or the upper limit of groundwater. A lot of times it's called the groundwater table as well. And humans definitely take note of where the water table is for a couple of reasons. One, if the water table goes below your pump in your well, then you can no longer extract water from your well, which is obviously a disaster. And two, the elevation of the water table within the subsurface also determines how groundwater is interacting with surface water. So if you think about the connection between a groundwater reservoir and a stream, if the water table adjacent to the stream is high, much higher than the stream, then you effectively have the groundwater flowing downslope beneath the surface into the stream and adding to stream flow. If the water table adjacent to the stream is below the stream bed, then you have the opposite effect, where water from the stream is actually infiltrating through the stream bed and then adding to the groundwater reservoir. So I should have denoted earlier when I was talking about the zone of saturation that the vadose zone and the zone of saturation aren't exactly the same. So the vadose zone is the area above the zone of saturation. So it's the area above the groundwater table. And so this includes not only the zone of soil moisture, where you have particles of water clinging to particles of soil due to molecular attraction, but it also includes an area known as the capillary fringe. And this is a region where groundwater is held in pore spaces by cohesion and adhesion. So cohesion is where water is sticking to itself, and adhesion is where water is attracted to and sticking to particles. And so the difference here between the capillary fringe and the zone of soil moisture is sort of detailed below here, where the pressure of cohesion and adhesion cause water to work against gravity. So effectively you have the water table, or the top of the zone of the zone of saturation, and then directly above that you have the capillary fringe, where you have water working against gravity due to the forces of cohesion and adhesion. And it's important to note that the smaller the pore spaces you have, the more capillary action you have, and the larger your capillary fringe is. So within the capillary fringe, you're going to have a higher percentage of the pore space filled with water than you would closer towards the surface in the vadose zone. So it's kind of an important distinction, because if you are trying to figure out where the water table is, you need to be able to tell the difference between the zone of saturation and the capillary fringe, which fortunately is pretty easily done in most wells. So let's zoom into these multiple layers of water in the subsurface here. So as just mentioned, and we'll start at the surface. If you move down below Earth's surface, you have some soil moisture, and then that exists within the unsaturated zone, also known as the vadose zone. And you can see kind of a close photograph of what that looks like, where you have water particles clinging on to soil particles, and then you have airspace in between. So you can have anywhere between a lot of soil moisture in the unsaturated zone to a little. Then when you continue to move down through the subsurface, down past the rooting zone of most plants, you get to the zone of saturation, which is where groundwater exists. However, again, just above the zone of saturation, you have the capillary fringe, where some water is working against the forces of gravity. But the main layers that you need to be concerned with in terms of thinking about how groundwater impacts both our lives and the lives of other plants and animals, the main layers you need to think about are the unsaturated zone and the zone of saturation. Oh, and so again, if you look within the zone of saturation at the groundwater, you can see that all the pore spaces between the soil particles are full of water at that location. And this is very important for wells, because if you have a well that's screened or open through the unsaturated zone and you're pumping in the unsaturated zone, you're not really going to get any water, because that zone doesn't have enough hydrologic conductivity, and therefore is not permeable enough, because you have water just clinging on to these soil particles, versus if your well has a pump and a screen, or is just open within the zone of saturation, then you can pull water from the surrounding area. And additionally, when it comes to connection with streams, if the unsaturated zone is adjacent to a stream, then the exchange of stream water and groundwater, or the exchange of stream water and subsurface water is much different than if you have groundwater adjacent to the stream. There's a lot more activity if there's groundwater there. So speaking of the water table and its impact on humans and other life, the depth of the water table is highly variable. Highly variable in any given location. It varies both seasonally and over time, or from year to year. And the depth of the water table is primarily impacted by changes in precipitation, both in magnitude and timing of precipitation, and snowmelt, and then also other changes to climate. For example, if it's much hotter, then more of that water might evaporate before it gets a chance to infiltrate through the soil. And then lastly, anthropogenic influences also greatly impact the depth of the water table. For example, if a farmer is pumping more water to irrigate their crops one year, or a city is diverting more water from a stream, and that stream happens to be losing surface water to the saturated zone or to the groundwater, then those sorts of things can make the depth of the water table deeper. Whereas, increased precipitation or cooler temperatures during the summer, for example, might decrease the depth of the water table. However, regardless of how the depth of the water table changes throughout the seasons or from year to year, the shape of the water table is, no matter where you are, is typically pretty much a subdued replica of the surface topography. So this means if you want to know where the water table is and you're standing on top of a mountain versus standing down in a valley, well, the water table is probably higher right beneath your feet when you're on a mountain than it is in the valley, because it's typically a subdued replica of the surface topography. So that's important to keep in mind, and it's also, a driver of groundwater flow. So when you have groundwater at a higher elevation underneath a mountain, and you have it at a lower elevation down in the valley, well, groundwater flows downslope the same way that surface water does typically. So that's important to keep in mind. So I've already mentioned a couple times that there's an interaction between groundwater and streams, and how this constitutes a very basic link in the hydrologic cycle. So I'm going to talk about a couple of terms and get into some greater detail on groundwater and stream interactions. So there are basically two types of streams as defined in reference to the ways that these streams interact with groundwater. One type are gaining streams. These streams gain water from the inflow of groundwater through the stream bed. So in the case of a gaining stream, you can think of the stream sort of gaining water that from the groundwater or from the saturated zone that seeps up through the stream bed and adds to the stream flow in that stream. Usually in the case of gaining streams, the water table near the stream is higher than the stream surface. So the reason why this would create a situation where the stream would gain water from the groundwater reservoir is because, again, groundwater flows downhill, and so if the water table near the stream is higher than the stream surface, then it's more likely to gain water from the groundwater reservoir, thereby increasing stream flow at that location. Before I move on, I think it's important to note that I'm talking about gaining streams and losing streams here, but any stream can gain water in some locations and lose water in other locations. And in fact, that's pretty much every stream. So you either have a gaining stream reach where, the water table is higher than the stream surface and groundwater is seeping up into the stream, or a losing stream reach, which is the opposite. However, an entire stream might be gaining or losing. That's called net gaining or net losing. Anyways, moving on to losing streams. Losing streams lose water to the groundwater system by outflow of the stream water through the stream bed. So again, this is the opposite of what happens in gaining stream reaches or gaining streams. And in this case, the water table is often lower than the stream surface. So, if you have water flowing through a channel and it's not connected to the groundwater reservoir, or it is connected to the groundwater reservoir, but the groundwater table slopes down, moving away from the stream, then you're typically going to lose stream water through the stream bed in that case, and that's a losing stream. One additional thing that's really interesting to note on gaining and losing streams is that not only do different reaches of the same stream gain or lose, but you can have the same reach of the same stream, and it can be gaining at one time in the day and losing at another time in the day. One common cause of that is actually vegetation near a stream, because during the day, vegetation is absorbing water through its roots, and some of that water might be groundwater that's moving towards the stream. And so during the day, the stream might be losing. Well, then at night, when those plants are no longer transpiring water and they're no longer absorbing water through their roots, then the same reach of the same stream might be gaining instead of losing. So just something interesting to note. So this slide shows, what gaining looks like and what losing looks like in different types of streams. So in part A of this figure, you can see a gaining stream where the adjacent water table is higher than the stream. And then in B, you can see a losing stream that's connected to groundwater. So in this case, the groundwater table slopes downward away from the stream, and even though it's connected to the stream, the stream is actually losing its water to groundwater. And then in scenario C, the lower part of this figure, you can see a losing stream that's disconnected. So this is when the stream is completely separated from the groundwater system by the unsaturated zone. But you're still having losses of water through the stream bed, and so that can ultimately infiltrate down and raise the water table locally underneath the stream. Okay, so we've talked a lot about the concept of groundwater in the unsaturated zone and gaining and losing of streams and stream reaches as a result of different interactions with groundwater. But what really are the physical factors that influence the storage and movement of groundwater? And these are important to understand when you try to fully understand the hydrology of a basin. So, for example, you can help plants or animals that are struggling to recover. You can figure out what's wrong with their habitat based on a hydrologic perspective, or maybe you want to determine whether or not it's a smart idea to allow an Amazon warehouse to move in and pump a lot of water out of the basin or not. Just a couple of random examples. So what are these factors that influence storage and movement of groundwater? The first one is porosity. So porosity is the percentage of pore space or open space in a rock or sediment. So if you think back to when we talked about the unsaturated zone, those spaces in between the sediment particles were pores. And the greater amount of pore space that you have per unit volume of a sediment or a rock, the greater the porosity is. The percentage of porosity depends on the size and shape of the grains of sediment, how the grains are sorted, and how tightly they are packed. So, for example, poorly sorted sediments typically have a low porosity because those sediment grains can pack in next to one another pretty well. Versus a well-sorted sediment, let's say like a coarse sand that's well-rounded, may have a high porosity because there's no way for smaller or different shaped sediment particles to pack in very easily. Because the particles are rounded and rather large, there's a lot of pore space left over, or a high porosity percentage. So porosity is really important because it determines how much groundwater can be stored. In other words, the storage capacity. So, let's say that you have groundwater in the subsurface, and in one location, let's say you have an acre field, and below that field, you have 100 feet of groundwater. And the interesting thing is that if you have 100 feet of groundwater underlying a 1 acre field, and if the sediment that groundwater is contained in has a low porosity, then you might not actually have very much water there, even though you have, 100 feet of groundwater. If you have 100 feet of groundwater and that just exists in some small fractures in some granite or some other type of bedrock, for example, that's not very much water. But if you have 100 feet of groundwater that exists within rounded gravel, then you have a ton of groundwater in that location. So that's important to keep in mind when evaluating groundwater resources. So this is a good sort of demonstration of porosity here. So the beaker on the left is filled with 1,000 milliliters of sediment, and the beaker on the right is filled with 1,000 milliliters of water. Now, if you move to the right, the sediment-filled beaker now contains 500 milliliters of water. The pore spaces, or the porosity, must represent 50% of the volume of the sediment in this case. Well, why is that? It's because you can see that the water is not any higher than the sediment, and you poured half of the water into that sediment, and it infiltrated through and filled the pore space. So that tells you that the amount of free space amongst that sediment is about 50% of its volume, or 50% porosity. Some other really important factors that influence the storage and movement of groundwater are permeability, the concept of permeability, and then features known as aquitards and aquifers, which are terms related to permeability. So permeability is the ability of a material to transmit a fluid. And this depends on the connectivity between pores. So, that free space, the pore space that's filled with water, how well connected are those pores? Because one thing that's really interesting is a lot of clays actually have an extremely high porosity because layers within the clays can expand and fill with water. However, clay particles are extremely small, so the connectivity between those layers in the clay sediment is very little, meaning that clays, despite the fact that they can store a lot of water or be very porous in some cases, are not very permeable. As opposed to that, as I sort of mentioned before, if you have something like a rounded gravel, that's extremely permeable because water in one pore space is very easily connected to water in another pore space. The water doesn't have to squeeze through any tight corridors where, the properties of cohesion and adhesion might prevent that water from moving, and it might sort of just stick to that sediment as we talked about, often happens in the unsaturated zone. A rounded sand is a pretty permeable material too in the world of, the spectrum of how permeable type of sediment might be. Okay, so I'm actually going to cover what an aquifer is first, since I just talked about sands and gravels. So an aquifer is a permeable rock strata or sediment that transmits groundwater freely. So sands and gravels are great examples of this. And they are good materials to build a well in, and you can pump water from sands and gravels rather easily. And sands and gravels allow for groundwater and surface water to interact with one another rather freely as well. The opposite of an aquifer is known as an aquitard, which is an impermeable layer that hinders or prevents water movement. An example of this is clay, so I guess I was getting a little ahead of myself here. But the clay particle size is extremely small, which means that water has to move through extremely small spaces to flow through clay. And as water has some molecular properties that create a desire. The water has basically a molecular desire to cling to other particles, and so in the case of clay, a lot of times water just does not really move through clay very well. In fact, a type of clay known as bentonite clay is often used to line wells in areas where you don't want any water coming into or escaping the well. It's also used to line landfills so that nasty materials within the landfill don't leach into the surrounding aquifer. So those are some great examples of clay working as an aquitard. So now that we've talked about permeability, it's important to go one step further and talk about hydraulic conductivity. I have this letter K equals hydraulic conductivity up here because for those of you who might go on to study hydrology or geology in any way, this is the letter that's used to represent hydraulic conductivity in a lot of equations like Darcy's equation that you'll have to learn how to use. Darcy's equation just allows you to calculate the discharge of an aquifer, and one of the variables in that calculation is hydraulic conductivity. Anyways, what hydraulic conductivity is the permeability of the sediment or rock strata plus the degree of saturation of that sediment or rock strata plus the density and viscosity of the fluid. So mostly, geoscientists worry about the hydraulic conductivity when they're thinking about water moving through some sort of sediment or rock strata. And so in this chart down below here, you can see the saturated hydraulic conductivity of water. So, we took out a couple of the variables in, how you determine hydraulic conductivity because we said, we don't care about the density and viscosity of the fluid because we're talking about water, which has a fairly consistent density and viscosity, although it does change some with temperature. And we no longer care about the degree of saturation because the degree of saturation is that these sediments or rock strata we're going to talk about are saturated. So in this case, the hydraulic conductivity is kind of the permeability is what it is. But anyways, I think this chart is really interesting because if you look at K, again, which is hydraulic conductivity, and let's look at feet per day, for example, here. So if you look down the chart, you can see that something like an unconsolidated sand and gravel that's well sorted, might flow as many as 10,000 or 100,000 feet per day. Water might flow that fast through an unconsolidated sand or gravel. And then, if you have something like that's an aquifer still, like the well-sorted sand and gravel, but it's a very fine sand, silt, loess, or loam. That's in that case, because the particle sizes are so much smaller, you can see that you have a drastic reduction in the amount of feet per day that water could flow through that type of sediment. So you're at a point of anywhere between 1 and 0.001 feet per day. It's a massive, massive difference, and it's extremely important to think about, not only in terms of connections between groundwater and surface water and the ability to pump groundwater, but also in terms of water quality. If you have an oil spill in one location, for example, well, if something can move 100,000 feet per day towards a river in one location, but it can only move 0.01 feet per day in another location, then if there's any way that you can get that spill to stay moving in the direction where it's only able to move 0.01 feet per day, then you have more time to do something about it, for example. Interestingly, if you continue down in the chart and you look at something like consolidated rocks, very highly fractured rocks can still have a very high hydraulic conductivity of 10,000 or 100,000 feet per day. And that's important to note because, some bedrock is very fractured and some is not. So if you look over to the right, in that same consolidated rocks category, you're looking at fresh granite, newly formed granite that hasn't really been fractured yet. And the amount of feet per day that water can move through newly formed granite, it's surprising that it can move through it at all, right? But it can, is 10 to the minus 7 feet per day. So it's a huge difference. All right, so I have another in-class activity for you to think about. So if the stream next to your family farm dries up, you may decide to drill a well because you still need water and you don't want to sell the farm or leave the farm, and you don't have any stream water anymore. So in this case, if soil is shallow and the bedrock is granite, could this work to drill a well here? And is there more information that you would want to know before paying to drill in this location? And if so, what types of information would you want? I'll give you a few minutes to think about this one, and then I will address it. Okay. So I'd be interested to hear your thoughts, of course, but these are my thoughts on this. If the soil is shallow and the bedrock is granite, could you drill a well to get some water for your family? In the case of, the stream next to your family farm drying up that you used to divert water from. I mean, the answer is yes, this could work. As we just saw on the previous slide, just because you have granite doesn't mean that that you don't have a high enough hydraulic conductivity to be able to pump water from that. So you would want to know whether or not the granite was highly fractured. Because if it was really highly fractured, then you could presumably drill a well and pump water from that granite. And if it was not highly fractured, if it was a young, fresh granite, then as you as you saw on the last slide, you're dealing with water moving 10 to the minus 7 feet per day. So you'd have to pump for a very, very long time before you got any water into your well, and that would probably not be worth the money. There's something else that you would probably want to know too. You would want, maybe a geophysicist or someone to come out and determine how deep the water is. And you would want to determine how the depth of the water, or the depth of the water table, changes over time. Because if the water is extremely deep, then you're going to have to pay a lot more money to drill that well. And if someone comes out and tells you, well, the groundwater table is 100 feet down, we can drill a well 110 feet down, and it sounds like you can afford it. It might sound like a good deal, but if groundwater levels fluctuate a lot seasonally in that location, as we just discussed before, that can definitely happen, then you may end up drilling a well and having your pump above the minimum water table level that you'll have every single year, and then during part of the year you wouldn't be able to pump water. So it's important to know both the hydraulic conductivity of the sediment or rock strata that you would be drilling into, as well as the depth of the groundwater table at that location and how that is changing over time and seasonally. So let's talk, sort of realistically about how groundwater moves on average here. So despite the fact that we've talked about some scenarios where groundwater can move thousands of feet per day, the average rate of groundwater movement, if you look, at a bunch of different types of sediment and rock strata, is about 4 centimeters per day, actually. So let's look at a simple groundwater flow system to think about this 4 centimeters per day. So the force of gravity and pressure differences move groundwater along the hydraulic gradient. So if you remember earlier in this lecture when I said that groundwater flows downhill the same way that surface water flows downhill, that's true, but it's slightly more complicated than that, because in some cases you have an aquitard that is confining groundwater, and so pressure builds up in that groundwater, and that pressure is equivalent to extra elevation. So in those cases, it's both the force of gravity, because groundwater wants to flow downhill, and the pressure differences that move groundwater, because if you have greater pressure in one location than another, then groundwater will flow from the greater pressure to the lower pressure as well. So both the force of gravity and the pressure are included in the hydraulic gradient. I hope that makes sense. Please feel free to ask questions if you have any about that. Also, in a simple, conceptual model of a groundwater flow system, groundwater is replenished in areas of recharge. So if you hear of recharge or groundwater recharge, that's where groundwater is being replenished. And groundwater flows back to the surface in areas known as discharge areas. So in an area where you have a gaining stream that's gaining water from the surrounding groundwater, that would be a discharge area. in an area where you have a ton of snowmelt and a ton of precipitation and no stream flow, that would be a recharge area. There's a term known as mountain block recharge. And that's because a lot of times up in the mountains, you get a lot more precipitation than you do down in the valley. And so generally that's an area of groundwater recharge. So this figure shows some examples of, common groundwater movement in a mountainous area divided by river valleys. So as you can see, you have recharge areas up in the mountains, and then you have gaining streams, which are discharge areas. So water is moving down hydraulic gradient from the mountains or the mountain blocks to the streams where it's discharging and then moving downslope on the surface. All right, so I'm going to talk about Darcy's equation or Darcy's law very briefly. This is sort of the mother of all groundwater equations that helps you to understand how groundwater moves. So what Darcy's law is a measure of the volume of water that flows through an aquifer using the hydraulic gradient, which we just discussed, which has components of the elevation of the groundwater and the pressure of the groundwater, using the hydraulic conductivity, or how permeable, essentially, the aquifer or aquitard is, and the cross-sectional area, or the area that the groundwater is flowing through. So let's look at this equation. So you have Q, which is a letter that stands for discharge, or discharge of groundwater, or the amount of water that is moving through the ground in units of length cubed, or let's just, to make it simpler for you right now, let's talk about it in units of cubic feet per second. So you have your groundwater discharge equals negative K, which, if you recall, is the hydraulic conductivity, times your dH divided by dL. So dH is the change in hydraulic head divided by the dL, which is the change in length. The change in hydraulic head divided by the change in length is the hydraulic gradient. So it's the slope of the water table. The reason why we say the change in hydraulic head rather than just the change in elevation of the groundwater is, again, because that term includes both the elevation of the groundwater and the pressure of the groundwater. And then lastly, you multiply it times A, which is the cross-sectional area. So kind of to recap here, the equation is discharge equals the negative hydraulic conductivity times the hydraulic gradient times the cross-sectional area. I wouldn't worry too much about the negative sign in this case. That might be confusing to some of you, but really all that that means is that the water is flowing downslope, and that's all. So just think about it as multiplying it times hydraulic conductivity times hydraulic gradient times cross-sectional area. So here's an example of the hydraulic gradient here. You have two wells. One well is labeled as H1, one well is labeled as H2. We're using wells here because a lot of times there's no way to tell what the elevation of the water table is unless you've drilled a well into the aquifer or into the saturated zone. So in this case, the hydraulic gradient is H1, the higher well, minus H2, the lower well, divided by D, which is the distance in between them. Or in the equation that I showed you on the previous page, dl, change in length. Okay, so let's do an activity related to Darcy's Law where you're going to calculate the discharge of groundwater. So let's say that your overly dramatic brother is concerned that the volume of water you might get from your well is not enough to sustain your new pet. Are his concerns warranted? Each of the 13 people in your family and as well as your new pet use 13 cubic feet of water per day. So remember the Darcy's Law equation. Q equals negative K times change in head divided by change in length times cross-sectional area. In this case, the material that you're dealing with where your well exists is highly fractured granite. And the height or the hydraulic head of the well up gradient from you is 500 feet, and the hydraulic head of your well is 400 feet. And the distance in between the well up gradient of you and your well is 5,280 feet. Your aquifer in that area, or the saturated zone in that area between your two wells, is 200 feet deep with an average width of 4,000 feet. So this is a lot to take in. So I'm going to walk you through it. So you're trying to solve for Q, which is the discharge of groundwater here. And again, you're trying to determine if, the 13 people in your family and your new pet that are trying to use 13 cubic feet of water per day will be able to survive using your well. So your discharge equals negative K. Now, what was K? K is hydraulic conductivity, and the material that water is flowing through in your location is highly fractured granite. So if we go to this table in the lower right, we can see that highly fractured rocks in the bottom left of that table, the slowest rate at which, the smallest K value that you would have is 100 or 100 feet per day. That's on the low end of the range. So we're going to use 100 feet per day as your K value to be conservative, because you want to make sure that you all can survive. Now, let's figure out what the change in hydraulic head is, the next part in the Darcy's Law equation. So you have H1 minus H2. That's the change in hydraulic head. Again, H1 is the well up gradient of you, and H2 is your well. So the change in hydraulic head is that you go from 500 feet in the well above you to 400 feet in your well. So that's 500 minus 400, that's 100. And then you need to divide your change in hydraulic head of 100 divided by the change in length between your neighbor's well and your well. And that change in length is D, which is 5,280 feet. And then finally, your cross-sectional area. So the aquifer in between these two wells has an average thickness of 200 feet and an average width of 4,000 feet. So to get area, you're going to need feet squared in this case. And so you multiply your average thickness of the aquifer of 200 feet times the average width of the aquifer of 4,000 feet. Yeah, I think that's 800,000 feet squared off the top of my head. So to put this all together to get your discharge, you're multiplying the K value of 100 feet per day. Remember I said don't worry about the negative sign. You've got 100 feet per day times 100 feet divided by 5,280, and then you're multiplying 100 times the product of 100 divided by 5,280 times what did I say? 800,000 feet squared. So I'm not a genius, so I don't know what that number is off the top of my head. If some of you do, then perhaps you should study math, or you're going to do very well in geology. However, the result that you're going to get is that, and this is important whenever you're computing any equation, and definitely important in geology as well, you want to make sure that the units that you get at the end of your calculation make sense. So you wanted Q a discharge, and you wanted that in a length cubed per unit time, because that's what a discharge is. And so in this case, everything was given to you in feet. So it'd be prudent to make the calculation as cubic feet per day, because everything that was given to you is in feet or in days. And hopefully that makes sense to you. I think probably when I do the remote field trip, I'm going to do a calculation like this for you on a whiteboard so that you can see exactly how I would calculate this out. But hopefully this is starting to make sense conceptually, why you need to incorporate the hydraulic conductivity of the movement of the material that the water is flowing through, as well as the change in hydraulic head between 2 points, as well as the cross-sectional area to determine the total volume of water moving through the aquifer per unit time. So one really important thing to keep in mind when you're thinking about groundwater systems and their connection with surface water systems is that groundwater moves in different scales. So the area of groundwater flow systems varies from a few square kilometers to tens of thousands of square kilometers. So a few square kilometers might be a really small catchment, like you go up into the Boise foothills and you see a tiny little stream that maybe flows for a few months out of the year. That would be a small groundwater flow system versus something that's tens of thousands of square kilometers. That's a massive groundwater flow system known as a regional groundwater flow system. And those systems interact with much deeper, larger groundwater systems. So I'm going to show a figure that displays what I'm talking about, because it's a lot easier to discuss in a visual format when a visual format is presented. So here we're looking at a hypothetical groundwater flow system. You've got a major river, and you can see that right next to that major river you have maybe some foothills. Well, water from precipitation and snowmelt is infiltrating into those foothills and then entering into the stream as the stream is a gaining stream in this reach. But then if you go further away from the stream, you can see rather than groundwater movement in a near surface local system, you also include groundwater movement in a sub-regional system. So if you go to the mountains on the other side of a lake next to this major river here, you can still get some groundwater in that sub-regional system making its way under the hills next to the major river And so that groundwater comes the whole way over there and interacts with groundwater from the local system there. And then finally, on the far right, the whole way on the other side of that other stream in the mountains there, it looks like the elevations are higher there. So maybe you've got some mountain block recharge from, higher mountains on the right of this figure. And that can feed into a deep regional groundwater system. So the black arrows in this figure denote sort of movement of groundwater that's very deep in the earth. And you can see that it still can make its way over the whole way towards underneath the major river on the left here. So it's important to think about kind of these three different types of systems and how often it might be that, the groundwater that is seeping through the stream bed and helping your local river or stream to gain water from the groundwater system, that might be from, local groundwater or locally sourced groundwater from snowmelt or precipitation really close to the river, for example. But if you were to drill a well in that same basin and you were to drill it deep, then you might be interacting with groundwater from a sub-regional or even a deep regional groundwater system. So that's all I have for you today. Is maybe you can hear my voice. I'm starting to lose my voice again. I hope you got something out of this lecture. Groundwater is a very important resource, both in terms of what we can as humans can use it for, but also in terms of the way that it feeds streams that are crucial to so much life on Earth. What I really didn't get to this week that I would have liked to have spoken more about is wells. So I encourage you, when you're reading this chapter in your textbooks and when you're studying for your final exam, to please read some more about wells, because they're important to understand. And whether you have a personal well or not, you're very likely to use well water for various purposes, because a lot of times city water can be derived from very large wells. So I wish you all the best of luck on your exam next week. As I've mentioned previously, will be the same format as the last exam, which is part of it is open book and part of it's not. And if you have any questions, please feel free to email me. And I hope you have a good week, and I will hopefully be feeling better next week and be able to do better with these lectures for you. All right, have a good one.